8 minutes ago, on top of a mountain in Chile, a machine the size of a small building did something that instantly started spreading across every space forum, every astronomy group, and every science page online. And before I tell you exactly what it captured, stay with me until the very end of this video, because the last part of this story is the part almost nobody online is actually explaining correctly. And once you understand it, you will never look at a breaking space discovery headline the same way again. Let's start with the basics, because you need to understand what this machine actually is before you understand why it just broke the internet. This is the Vera Rubin Observatory. It sits on top of a mountain called Cerro Pachon, high in the Chilean Andes, one of the driest and darkest places on planet Earth. Astronomers chose this exact spot on purpose. No clouds, no city lights, no moisture hanging in the air to blur out the stars. It is, quite literally, one of the best possible places on the entire planet to point a lens at deep space. Now here's where it gets interesting. This observatory is not just another telescope sitting on a hill. Its main mirror is 8.4 meters wide, almost as wide as a tennis court is long. Attached to that giant mirror is a camera, and not a normal camera, not even a professional camera. This is the largest digital camera ever built by human beings. It captures images at 3,200 megapixels. Think about that for a second. Your smartphone camera has somewhere around 12 to 50 megapixels. This single camera has 3,200. Every photo this telescope takes is so massive, so detailed, that if you wanted to display one full image at its true resolution, you would need about 400 separate 4K television screens lined up side by side just to show one picture. And here is the part that really shows you what this machine is capable of. This telescope does not take a slow, careful photo once in a while, the way older telescopes do. It moves fast. It captures a brand new, incredibly detailed image of the sky roughly every 40 seconds. 40 seconds. Then it swings to the next patch of sky and does it again, all night, every night, capturing close to 1,000 images a night, for 10 years straight without stopping. Why 10 years? Because the real mission behind this observatory, the one everything has been building toward for 2 decades, is called the Legacy Survey of Space and Time, or LSST for short. The plan is almost impossible to picture. Instead of taking a single snapshot of the universe, Rubin Observatory is scanning the entire southern night sky in ultraviolet, visible and near-infrared light, over and over, roughly every 3 days, continuously, for an entire decade. Stitch those images together and you don't just get a picture of the universe, you get a movie. A real, honest-to-goodness movie of the night sky changing in real time, made from actual observations, not animation, not simulation. Scientists working on the project have called it the greatest cosmic movie ever made. And on June 30th, 2026, that movie officially started rolling. But before we get to the discovery that just sent this observatory trending everywhere, let's rewind for a moment, because this telescope carries a very human story in its name, one that most people scrolling past the headlines never stop to learn. This observatory is named after a woman called Vera Rubin. She was an American astronomer who, decades ago, was studying how galaxies rotate, and she noticed something strange. Galaxies were spinning in a way that should not have been possible if you only counted the visible matter inside them. The stars, the gas, the dust we can actually see through a telescope. Based on visible mass alone, the outer edges of a galaxy should spin much slower than the inner regions, the same way planets far from the sun move slower than planets close to it. But that is not what Rubin found. The outer stars in these galaxies were spinning almost as fast as the inner ones. Something invisible had to be out there, adding extra gravity, holding those galaxies together from the outside in. Her careful, patient work became some of the strongest evidence scientists ever had for the existence of what we now call dark matter, a mysterious substance that gives off no light we can detect, yet appears to make up a huge share of the mass in our universe. Vera Rubin spent her entire career being precise, careful, and completely devoted to watching the sky and trusting what the numbers told her. So when the National Science Foundation and the Department of Energy built the most advanced survey telescope in history, they named it after her. And it fits, because this observatory exists in many ways to continue the work she began, chasing answers about dark matter and its strange partner, dark energy, the mysterious force that appears to be pushing our entire universe to expand faster and faster with every passing year. Now let's actually talk about what happened, because this is the part everyone online is reacting to right now. On February 24th, 2026, Rubin Observatory issued 800,000 alerts to astronomers around the world in a single night. 800,000 separate events flagged in one night alone. New asteroids appearing, stars suddenly exploding as supernovae, distant supermassive black holes flaring as they feed on surrounding material, and variable stars whose brightness rises and falls over time. Astronomers call this the true beginning of the alert stream, one of the final milestones standing between the observatory and the official start of its 10-year mission. And that is exactly what makes the most recent moment so significant. Because once the survey officially began on June 30th, 2026, following years of construction, testing, and a careful operational review of technical readiness, data quality, and calibration accuracy, the observatory did not slow down. It sped up. From that night forward, Rubin Observatory began scanning the entire southern hemisphere sky over and over every 3 days, collecting close to 10 terabytes of data every single night, with some estimates placing that figure even higher once the survey reaches full operating speed. Across the full 10 years, the observatory is expected to generate roughly half an exabyte of information in total, an amount of data so enormous that entire teams of scientists and engineers have spent years building the algorithms needed to sort through it. Scientists have said the amount of data Rubin gathers in just its first year alone will be greater than everything collected by every other optical observatory on Earth combined. Not close to it. Greater than all of them put together. Before we go further, it helps to understand how this camera was actually built, because the engineering behind it is its own story. The LSST camera, the heart of this entire observatory, was constructed by the U.S. Department of Energy's SLAC National Accelerator Laboratory, working alongside teams from around the world. It is roughly the size of a small car and weighs around 3,000 kilograms, yet it has to operate with such precision that it can capture faint, distant light without the smallest vibration throwing off the image. Inside it are 6 large optical filters, each one designed to capture a different band of light, from ultraviolet all the way through to near-infrared, allowing scientists to study everything from hot young stars to cool, faint, distant galaxies in a single coordinated survey. Every image the camera takes has to pass through layers of calibration, checking focus, checking exposure, checking alignment before it becomes part of the official data set. This is why the commissioning phase took as long as it did. A mistake at this stage could ripple through 10 years of observations. The team behind the project has been very open about this. They have said the decision to officially begin the survey only came after careful operational review covering image quality, survey speed, system uptime, reliability, and calibration accuracy. Because once the 10-year clock starts, there's no going back to fix small errors. Now, here is where the story turns into what the internet is actually reacting to. During the early testing window known as the early optimization surveys, astronomers working with Rubin Observatory discovered over 11,000 brand new asteroids in just about a month and a half using nothing but early test data. 11,000 in 6 weeks. That stands as one of the largest single batches of new asteroid discoveries ever submitted to the International Astronomical Union's Minor Planets Center, the official worldwide body responsible for verifying and cataloging small objects across our solar system. Inside that group, scientists identified 33 near-Earth objects, asteroids, whose orbits bring them relatively close to our planet. None of these newly found objects pose any danger to Earth, but tracking near-Earth objects remains one of the most important jobs any observatory can do, because the more we know about them, the better prepared we are for the future. On top of that, Rubin's early data also revealed 380 new trans-Neptunian objects, icy bodies that orbit far beyond Neptune, out in the cold, distant edges of our solar system, where sunlight takes hours just to arrive. 2 of these newly discovered trans-Neptunian objects have extremely stretched, elongated orbits that carry them nearly 1,000 astronomical units away from the Sun at their farthest point. 1 astronomical unit equals the distance between Earth and the Sun, so these 2 objects travel almost 1,000 times farther from the Sun than we do. That is deep, remote territory. Researchers believe studying orbits like these could eventually help confirm or rule out the long-debated theory of a hidden 9th planet, sometimes nicknamed Planet 9, possibly 5 to 10 times more massive than Earth, potentially warping the paths of distant outer solar system objects. One planetary scientist involved in the project has said that even if Rubin cannot spot the planet directly, finding more objects with warped orbits would still be an important clue pointing toward its existence. The same early batch of data also allowed scientists to refine and correct the orbits of more than 80,000 asteroids that were already known, objects tracked before, but whose paths through space were not fully precise. With Rubin's frequent, detailed observations, astronomers sharpened those orbital calculations, making our entire map of the solar system more accurate than it has ever been. Then, in early 2026, something else turned heads across the astronomy community. Using data gathered during the observatory's first look period, scientists published the very first peer-reviewed scientific paper based on observations from the LSST camera itself. What they found was genuinely record-breaking. Hidden inside the data was the fastest spinning asteroid larger than 500 meters wide ever recorded, sitting quietly in the main asteroid belt. Researchers said an object like this simply could not have been detected without the unique speed and sensitivity built into Rubin's camera. This is also the moment worth pausing on, because it is easy to miss just how fast this observatory works compared to everything that came before it. In just over 10 hours of test observations, before the real survey had even officially begun, this telescope had already captured millions of galaxies and Milky Way stars, and had already spotted thousands of asteroids inside our own solar system. 10 hours. Most observatories take years to build a catalog like that. Rubin did it in less than half a day of testing. So why is this observatory suddenly everywhere online right now? Because once the survey reached full operating speed, this system began sending out as many as 7 million alerts every single night. 7 million. And each one represents a real change happening somewhere in the sky. An asteroid shifting position, a star exploding, a black hole flaring, a distant galaxy changing in brightness. One of the deputy directors of Rubin Operations said that millions of alerts in just the first couple of months alone already proved the observatory is up and running as a genuine discovery machine. Teams are using artificial intelligence and machine learning systems specifically built to sort through this flood of information in real time, because there's simply no way a group of human astronomers could manually review 7 million nightly alerts on their own. The AI filters through the noise and flags the events that matter most. So researchers around the world can react quickly, sometimes within minutes, and turn other telescopes toward whatever unusual event Rubin just detected. This is part of what scientists call multi-messenger astronomy, studying the universe using multiple types of signals at once: light, gravitational waves, and cosmic rays working together. When Rubin spots something like a possible collision between two extremely dense objects, or a sudden explosive event somewhere in the sky, it can immediately alert observatories around the globe to point their instruments at that exact spot, so the event can be studied from every possible angle before it fades away. Supernovae are one of the clearest examples of why this speed matters so much. A supernova is what happens when a massive star reaches the end of its life and explodes in a burst of light so powerful it can briefly outshine an entire galaxy. These explosions do not last long. They brighten quickly and then fade over days or weeks, which means if you're not watching the right patch of sky at the right time, you simply miss it. Older telescopes, moving slowly and covering small patches of sky, missed enormous numbers of these events simply because nobody was looking in the right place at the right moment. Rubin Observatory solves that problem by never really looking away, because it revisits the same regions of the sky every 3 days. Every single explosion, every sudden flare, every fading afterglow gets caught somewhere in that repeating cycle of images. The moment the system detects a sudden change in brightness that matches the pattern of a supernova, it sends out an alert within minutes, giving astronomers around the world the chance to point other instruments at that exact location while the explosion is still happening. Phil Marshall, the deputy director of Rubin Operations for SLAC, described this entire journey in a simple, honest way. He said it took 20 years of hard science, engineering, and determination just to reach the point where the team could finally call action and start rolling on what he described as this blockbuster movie of the universe. He also pointed out that the millions of alerts generated in just the first couple of months of testing already proved the observatory works exactly as intended. A genuine discovery machine, fully assembled and finally switched on. Mike Brown, a planetary scientist at Caltech who has watched this project develop since his early days in graduate school more than 2 decades ago, said working with Rubin's data now feels like something he could only have dreamed about back then. Watching a project take shape over 20 patient years and finally become real, working, functioning science. He also pointed out something worth remembering, that if you ask 50 different astronomers what they are most excited to find using this telescope, you would likely get 50 completely different answers, because this one survey genuinely touches nearly every corner of modern astronomy and astrophysics at the exact same time, all at once, every single night. Over the coming 10 years, scientists expect this survey to reshape what we know about our own solar system in a fundamental way. Researchers predict Rubin could help triple the total number of known asteroids and increase the number of identified trans-Neptunian objects by nearly 10 times what we currently know. Every single discovery adds another piece to the puzzle of how our solar system formed billions of years ago, how planets and smaller bodies settled into the orbits we see today, and to what forces shape the outer edges of our cosmic neighborhood. But the larger goal, the reason this observatory carries Vera Rubin's name in the first place, reaches even further than asteroids and comets. Scientists are hoping this 10-year survey finally delivers real answers about dark matter and dark energy, the 2 biggest unsolved mysteries in modern physics. Dark matter appears to make up roughly a quarter of everything in the universe, yet we have never directly seen it, only its gravitational fingerprints on galaxies, the very same fingerprints Vera Rubin first noticed decades ago. Dark energy is even stranger. the mysterious force that seems to be causing the expansion of our universe to accelerate rather than slow down the way gravity alone should cause it to behave. By watching billions of galaxies over 10 full years, tracking how they move, how their light shifts, and how the structure of the universe evolves over time, scientists hope Rubin Observatory can finally help explain what dark matter and dark energy actually are, something no telescope in history has fully managed to answer. So now think about everything this single machine is doing at once. It is mapping our own solar system in more detail than ever recorded. It is discovering tens of thousands of new asteroids, some of which may one day matter for planetary defense. It is catching supernovae the moment they explode, giving scientists a front row seat to some of the most violent events in the universe. It is tracking supermassive black holes as they flicker and flare across billions of light years of space. It is building toward a full catalog of an estimated 20 billion new galaxies. And underneath all of that, it is quietly gathering the exact kind of data that could finally crack open two of the biggest mysteries human science has ever attempted to solve. And we are still only in the earliest days of this 10-year mission. Everything described in this video, the 11,000 asteroids, the record-breaking spinning space rock, the 800,000 alerts in a single night, the 7 million alerts a night once full speed was reached, all of it happened while this observatory was still just getting started. The real 10-year clock only began ticking on June 30th, 2026. Every single night from here forward, this telescope keeps watching, keeps scanning, keeps capturing data at a scale no observatory on this planet has ever managed before. And somewhere in that flood of nightly images, hiding among millions of galaxies and thousands of newly discovered asteroids, there is a very real chance that Rubin Observatory ends up capturing something completely unexpected, something nobody predicted, simply because it is watching the sky more closely, more often, and in more detail than any instrument in the history of astronomy. Remember, this observatory is only a few weeks into a mission that is supposed to run for 10 full years. Every single one of those years is going to bring fresh batches of asteroid discoveries, fresh supernova alerts, fresh images of galaxies nobody has ever cataloged before, and slowly, piece by piece, real progress toward finally understanding dark matter and dark energy, the two mysteries that gave this telescope its name in the first place. If this kind of real, fact-based space coverage is something you genuinely care about, make sure you hit that subscribe button right now, because we are going to cover every major update from this observatory as it happens across the next 10 years. Drop a comment and tell me which part of this story surprised you the most. The 800,000 alerts sent out in a single night, the fastest spinning asteroid ever recorded, the 11,000 new asteroids found in just 6 weeks, or the fact that this telescope can now send out 7 million alerts every single night once it reaches full operating speed. I read every comment, and I genuinely want to know which fact made you stop and rewatch a section, because that tells me exactly what kind of space stories to bring you next. And if you learned something new today, share this video with someone who still thinks space exploration slowed down after the moon landing, because right now, in real time, we are living through one of the most productive periods in the entire history of astronomy, and this observatory in Chile is at the very center of it. Thanks so much for staying with me all the way until the very end. I will see you in the next one.